So let's get started. We are now recording, so I will conduct my testimonial to the world of YouTube, and I will thank my steel design class for bringing me a cake for my 30th birthday. So I do appreciate that. The picture from Facebook on the cake was was especially interesting. I think we've gotten a fair number of pictures of it, so I think it's fairly immortalized. So here's what I'm going to do. I'm just going to sort of slowly get back into the world of steel, and if you all would like, there's napkins and plates and forks. I guess you all or somebody can coordinate, and you all can help yourself. I'll let you all sort of handle that. Whoever wants to handle that. I don't know if Stuart, if you want to take care of that, or if somebody else wants to. Anybody who wants, you can have cake while we talk about fillet welds. Well, I might have some either in between class or a little bit after, but
you do have to be the first one.
okay. Okay. To just make the first cut, I guess. All right. So, hold on. This is not the samurai sword or lightsaber, but this will be added to the repertoire for sure. So I'll just make sort of a cut right here. How's that? I don't know. It's covered. All right. So, all right. I just made a little cut off the corner. It's probably a somewhat medium-sized piece. I mean, how we want to do this? Somebody want to help serve, or? Okay. Have you got this? Okay. All right. Well, since you're doing this, you can have the first piece. Okay. All right. You'll be. All right. So I guess. Yeah. 17th. You're right. Yeah, that is the 17th. Thank you. So I will let Mr. Cruikshank sort of handle the cake dispersal process. I am going to go through announcements, though, and I am going to sort of continue the try and at least get some stuff done with steel. Okay, so let's just make sure everybody's aware on a couple things. Just trying to get back in business. It's like I do genuinely appreciate it, though. I really appreciate the gesture. It's pretty awesome. I'm not forgetting this one anytime soon. All right, so we have our exam. We do still have our exam. I know that the cake like. We do still have the exam coming up on Wednesday, March 15th. So I've got the binder. And what I've got the attendance sheet in the binder. I'm going to pass this around. If there's anything that you're missing, just let me know on the sign-in sheet, and I'll leave that here. Okay. Let's see, what else? I have homework 5 for you, and you're going to think I have a typo, and I don't, because homework 5 has one problem on it. But if you, once we get to fillet welded connections and started getting into design and into balance welds, you'll see that this one problem essentially has everything that we need. Like if I assigned any more problems, it would just be busy work. So there's only one problem on the assignment. It's incredibly short, but this one problem covers everything you need to know with welds. So what I'm going to do is I'm going to pass this out. Let's see, 1, 2, 3, 4, 5. It's also uploaded. Oh, yeah. Well, here, I'll do this, and then I will do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nine, and then these two right here. Okay, so, got it. This is, like I said, it's a pretty short assignment, but it's due on the 10th, so you got plenty of time to do that. Our exam's on the 15th. We'll have a review session on Monday. So my goal is to get the homework graded and back to you that Monday. If not, I'll at least have the solution ready for you. And then we'll have our exam on Wednesday, and then assuming we don't have any blizzards between now and then, we'll cancel class on the 17th. So does that sound fair? Yep. Okay, all right. So today we're going to get into design of welded connections. We're going to be specifically doing fillet welds, and we're also going to get into balanced weld design, which is just a, excuse me, just a way of proportioning fillet welds for members that don't have a central axis of symmetry, or their centroid doesn't lie along their symmetrical axis. Okay. Whew. Once this loads up, let's do this. Okay, so while we are getting sort of squared away into the world of steel design and cake, let me take a moment and sort of briefly review just the general analysis and design procedure for welds. Let me go back to the actual capacity for welds and go to this. So we have our nominal capacity and design capacities for fillet welds according to their weld metal capacity and their base metal capacity. And for base metal capacity, we have shear yielding and shear fracture. Hopefully you found that after the last example that we did, that the analysis of a welded connection is an incredibly straightforward one, right? Well, design is just as straightforward, okay? Now with bolts, let me skip ahead to right here. So with bolts, we determine the design load. We divide it by the capacity of a single bolt to get the total number of bolts. Well, with welds, we divide by the capacity of one single inch of weld to get the total number of inches, and then that's really it. We do have to use the weld limitations that we explored last time to determine a weld size. So if you recall, our weld limitations came from a minimum from a table in the spec and a maximum based on T or T minus 1/16 of an inch. Using that, we pick our appropriate weld size. We want our weld size to be as big as possible without going over 5/16. Now, I mean, if you're going to need like a 3/4 inch weld or something like that, awesome day, just cake, right? Awesome stuff. When in doubt, you don't want to go over 5/16 because that's about the largest weld that you can get in a single pass. You do want large weld sizes, though, because a large weld size indicates a short weld length. And in the end, that's going to be quicker to deposit, which is going to mean less time, less labor, less cost. So yeah. Any questions on that or on the analysis of a connection that incorporates fillet welds? Everybody okay with that? Okay, well, if you can do that, then I want to tackle design. I think you're going to find the design pretty straightforward. I even have the answer right after this because the answer incorporates 5/16 inch welds that are 6 inches long on each side. But I want you to see where we get that. Sound good? Okay, now, we're unlike, another thing, unlike bolted connections, we are not going to need to go back and check the base metal. If you recall, when we did bolted connections, we used bolt shear to design the connection, but then we had to go back and check bolt bearing. Well, we really don't have to do that with the way that fillet welds work because we can actually check the base metal and the weld metal kind of all at the same time. But we'll see that as we get into this. All right, so any questions? All right, let me see something. Okay, so do you want me, are you two good? You're, 2 more pieces? Okay, well, I'll sort of slowly take my time, and I think a lot of this will be pretty straightforward to roll with. So we have E70 electrodes that we're going to be using to deposit a fillet welded connection on the plate shown below. So we have a 6 by 3/8 inch plate that we are welding. We've got A572 grade 50 steel that's used, and we have a dead load of 15 kips and a live load of 40 kips. Again, when in doubt, we are making the assumption that all the live loads are reduced and we don't need to worry about that. So what we're going to do is, I think the procedure is going to be pretty straightforward. You know, factor the load, go into weld sizes, and go from there. Okay. So I'll take my time, at least at the beginning. I'm good? Am I good? All right. All right. Example 13. So we have a dead load of 15 kips and a live load of 40 kips. So the first thing that we need to do is factor those loads, right? So we have 1.2 times the dead plus 1.6 times the live. 82 kips. What was that? What's that? We did? Maybe I was thinking maybe I forgot to save or something. Well, let me go ahead and just sort of check that out. 1.2 times 15 kips plus 1.6 times 40 kips. If anything, I think just by muscle memory, when you all get out of here with your degrees and you're in the workforce and somebody says, like, this much dead load and this much live, 1.2 dead plus 1.6 live, it'll just, you know, it'll just roll off the tongue. Oh, oh,
Maybe like a POW. They just insult their number.
oh, all right. That was, I don't think that steel design, does, I don't know if it incites much post-traumatic stress or anything like that. It's not that bad.
No,
Post-tensile stress disorder, right? That's a good one. Okay, so we've got our factored load of, of 82 kips. What we need to do is we need to determine our weld limits. So what I want to do is I want to use minimum and maximum weld limits to select a size for the a given weld. So let's look at weld limits. Now, weld limits are going to be a function of the plate thickness. So what I'm going to do is I'm just going to sort of put down here that the thickness of the plate is what? 3/8. So we're going to need an A min and an A max. Now, A max we calculate, but A min we get from a table. So that table is in section J2 of the spec. So if you have a plate that is 3/8 of an inch thick, what is the minimum weld size according to the spec? Quarter of an inch? Is it quarter? I got 3/16. Is everybody else? No, it's not. Distracted by cake, yeah. I will definitely entertain that excuse for today. I don't know about that one. And we don't have tests, we have celebrations. We have celebrations apparently on multiple occasions. So that's in the manual on 16.1-111. Okay, now A max is computed as either the thickness or the thickness minus a 1/16 of an inch, and that depends on where the plate is in reference to a quarter of an inch. This is bigger than a quarter of an inch, so that's T minus a 1/16 of an inch, so 3/8 minus 1/16. And the Casio will do those fractions for you, and you should get 5/16. So let me ask you a question. If you have a minimum weld size of 3/16 and you have a maximum weld size of 5/16 and you're in design mode, what weld would you use? 5/16. Yeah, go with the bigger weld. It's going to be a shorter weld. So we'll say use A equals 5/16 of an inch. Okay. Because what if it was what if the minimum was bigger than 5/16? So you need to know what that is. So you need to know in terms of number of passes. Your minimum and maximum, well, let me say this. You make a good point, unless you've got a really, really thick plate, which is possible on some connections. I would argue your maximum in your scenario is probably more important. Because if your maximum was only like 1/4 of an inch, then you can only use 1/4 of an inch. But if your maximum is over 5/16, then you can just go with that. You do make a good point, though. But yeah, I would say that the minimum is probably going to be more important in scenarios where you have like really, really thick plates, something that's like 1 inch or 1.5 inches or something like that, which we do see. So, all right, sound good? All right, so here's what I'm going to do. I'm going to compute the capacity of 1 inch of weld. Okay, so in order to compute the capacity of 1 inch of weld, I need a few things. Okay, so I've got A is 5/16 of an inch, because that's what I got from my design scenario. Help me out. What's FEXX going to be? 70 KSI, because we're using E70 electrodes. Okay, now the length of the weld in this instance is going to be 1 inch, and the thickness is 3/8. That's the thickness of the plate. Okay, so we can compute a couple quantities, I think, right now. So, we do need a couple things. What's FY and FU going to be for A572 grade 50 steel? 50 and 65. Yeah, FY is 50, FU is 65 KSI. So that, so I'm going to go ahead and write that. So FY and FU, and we will say that that is table 2-4. Oh. Okay. All right. So we can go ahead and start to compute capacities. Before I do that, though, since I've got the length of the weld and I have the thickness, I can then compute the gross net area in shear, which if I have a single inch of weld and I have a thickness, I mean, how am I going to compute gross and net area? Just multiply them, right? So I propose that the gross and net area in shear are just the length of the weld times the thickness, so 0.375 inches squared. So that's just 3/8 times 1. All right. Sound good? Well, if you've got these quantities, you can compute the capacity of an inch of weld according to base metal yielding, base metal fracture, and the weld metal. So let's just do those one at a time. So weld metal capacity is phi RN is phi times 0.60 FEXX times 0.707 ALW. All right, so we have everything, and it's really just a plug and chug. So what is phi for weld metal? Yep. 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 So 0.6, and then we have FEXX, which is 70 KSI, right? We have, this is 0.707. We have this is 5/16. And we have our length of our weld is 1 inch. So plug and chug and tell me what you get. We'll just keep it to something like 2 decimal places. 6.96 kips, right? All right, do I have a second on that? Okay, so this is 6.96 kips, but I'm going to actually write out for 1 inch of weld. All right, Sound good? That's not bad, right? Okay. Let's do base metal capacity. Now there's two base metal capacities. There's base metal yielding. So phi Rn is phi times 0.6 Fy AgV. So that is a phi of, now what is phi for base metal yielding? 1. And then 50 KSI, 0.375 inches squared. So what do we get for this? 11.25. Do I have a second on that? All right. So this is 11.25 kips for 1 inch of weld. And then our next one is base metal fracture. So phi Rn is phi times 0.6 Fu AnV. So phi for base metal fracture is 0.75. So 0.75 times 0.6 times 65 KSI times your area. So. And then what does that come out to be? 10.97. Okay, so let me ask you this. If you were asked what is the capacity per inch, is it the 6.96, the 11.25, or the 10.97? 6.96. That's the lowest one, right? The lowest one's what's going to govern. So if I load this connection, what's going to happen is that the weld metal is going to fail first. That make sense? All right, so here it is. So does everybody have all of this? All right, no, that's fine. I'll give it a Oh, but this one's simple. I mean, this isn't that bad, though, is it? But all that sugar should give you all that energy, right? Getting a toothache. Has everybody got this? I will have some. That is for sure. All right. Everybody good? Okay, so therefore, if I'm reporting the capacity, the phi Rn is this one right here, the 6.96 kips, and I'll say kip per inch. Okay? So if you've got that, then all you've got to do is the following. So therefore, the length of weld required is just Pu over phi Rn. So here's the long and short of it. The factored load was 82 kips. And the weld, according to weld metal capacity and base metal capacity, can withstand 6.96 kips per inch. So dividing that, what do we get? 11.78 inches. Everybody see that? So here's your connection. Since it's a plate and it's just a rectangular cross section, let's just keep it simple and do half and half, and then we'll say, all right, then we have 5/16. It's a fillet weld, and it's 6. And that's it. That's all there is to it. That's pretty simple, isn't it? You actually don't need to, because it's understood on weld terminology that that 5/16 is in inches and the weld length is in inches. I mean, if you want, that's fine. I mean, I can put, I can go ahead and say that this inches and in inches. You don't have to. It's sort of implicitly understood. But don't get me wrong. The last thing I'm going to do is fault somebody for no, these are the units. I'm going to be totally okay with that. Any questions? Yes. If it's, I mean, it'll indicate, you know, draw a schematic, then yeah. I mean, I won't be ambiguous. I don't think I am, though, on stuff like that. Like I'll say, you know, draw out your schematic, indicate it. As a follow-up, bring a straight edge. No, seriously, straight edge will help. I mean, it'll help on your exam. All right, sound good? So if you understand that, then I think you'll understand what comes next pretty easily, because it's pretty straightforward. So when we laid out that connection, we got a length of 11.78 inches. So we said, all right, let's just round it up to 12. Well, let's cut it in half. Let's say half goes up here, half goes down there, and that's our connection. And I think that's pretty simple. You know, think about it like this. You got a plate. I mean, think about it. It's just a plate. You're yanking on it. So put half the weld over here, half the weld over there. Makes sense, right? The problem is, what if you have an angle? If you have an angle, it's not as simple as that, because the angle, it's not like a plate where the centroid's right down the middle. The centroid for an angle is somewhere like right here, okay? So if you assume that the load goes through the centroid, it's a lot like a beam. You know, if this is a beam, and I've got a support here and a support here, and I'm sitting like right here, most of the reaction is on this side, not over here, right? So wouldn't it stand to reason that if you're assuming your load is not going through the halfway up and down, but it's actually going through the centroid, that you'd actually need more weld along that side than you would the other. So if you try and lay out a welded connection to where you're assuming the load goes through the centroid, and therefore you're placing more weld on one side than you are the other, we call that a balanced connection, or a balanced weld. We're really trying to eliminate any potential bending in the angle. And there's some really distinct areas where you want to do that. I mean, first, I'd like to do that just in general if I've got the room and the geometry in order to do a balanced weld. When in doubt, I'd like to do it. Just because that way I know that the angle is behaving according to the principles that I've used when I designed it. But there are some really specific instances, like for instance in fatigue. We definitely like to use balanced welds in fatigue, because if you don't, you can exacerbate the stresses on those welds a little bit. And as we saw from our McDonald's video, welds and fatigue don't really get along very well, right? So I try and avoid that whenever we can. Sound good? So we're going to do another example. It's going to be very, very similar to the one that we just did, but once we get to actually laying out the connection, it's going to get pretty different. So I'm probably going to go through the beginning parts of it pretty quickly, but I think you'll kind of see why I'm going about it in that fashion. All right, so we've got a factored load. In this case, instead of giving you a dead load and a live load, you all know how to do that. So a factored load of 150 kips. We're not worrying about the gusset plate, so we have a 6 by 4 by 3/8 inch thick angle. Now, if you notice, look at this. I'm using the same steel, right? Think about it. Same steel, A572 grade 50, E70 electrodes, and it's the same thing over here. Same steel, same electrodes, same thickness, okay? So because of that, I can tell you right now, capacity of the weld, 6.96 kips per inch. Everything's the same, right? But we'll walk through some of those quantities just to ensure that we're all fine with that. But I'll probably be pretty brief on some of that stuff. All right, sound good? So again, I did this particular example is like that on purpose, okay? The same thickness, the same steel, the same same electrode. So example 14, all right, so we'll say our factored load is a PU value of 150 kips. Did you have a question? Oh, okay, sorry. All right. Our material properties, we have FEXX is 70 KSI. We have FY is 50 KSI. And we have FU is 65 KSI. Okay? Just like last time. Okay? Now, when it comes to our weld limits, okay, when it comes to our weld limits, our Amin is again going to be 3/16, and our Amax is going to be T minus a 16th, so 3/8 minus a 16th, which is 5/16. So again, just like last time, same story. Right. Is everybody okay with that? Hopefully that's pretty straightforward. And then all I'm going to do for capacity for 1 inch of weld is this. So I'm going to say the thickness is 3/8 of an inch and the length of the weld is 1 inch. So weld metal capacity is 6.96 kips per inch. Did I mess something up or? No, you're fine. I am going through this kind of quick, so.
I was just saying, like, you always use plastic. You always try to use plastic.
Yeah, because 5/16 is about the largest weld that you can deposit in a single pass. If you go bigger than that, what's going to have to happen is, like, if you're using something like a MIG welder, and let's say you've got something like a 3/4 inch weld, then you're going to have to pass and then pass again, pass again. I would try to. Now, let's be clear. Our range is like 3/16 to 5/16, so it's a pretty tight range, and yeah, I'm going to go with 5/16. But if we've got something like a 1.5 inch thick plate, which is not that unheard of in our world, and you've got a minimum and maximum range between like 3/4 and an inch, I mean, well, you're going to have, in that scenario, your loads are probably pretty significant. You're going to have multiple passes anyways. And I would just try and do your best to reduce the number of passes, and that comes a little bit from experience, a little bit with keeping in contact with your fabricator and your welder to ensure that you're using a weld that makes sense. Most, I would say, structural connections in buildings, though, things like beam-to-beam connections and beam-to-column connections, like very typical ones, you can get away with doing something like a 5/16.
That's the max for one pass.
One pass, yes. And I'll say, you're not really going to find that you're going to be hard-pressed to find that in a spec. That's more just known. So, yep. It might be in the commentary, though. I'm actually not sure on that. So, yeah, E70 electrodes, those are very common, yes. Those are very common in structural design scenarios, yes. Sound good? E70s and E60s are pretty common, too. I mean, they make all the way to like E80s, E90s. I think they even make E110s, but, I mean, you're talking about some expensive and some serious welds there anyways. Sound good? All right, so base metal capacity will be yielding. I know we're writing a lot of the same stuff, but I just want to make sure that everybody's aware of the process. And base metal fracture. Didn't we say it was like 10.97? All right. I'm writing out the process, but I'm doing it expeditiously because what I don't want to have happen is you're doing something like a homework and the answers change, and then you go, or the dimensions change, like, wait, how did he come up with these values? Well, I wanted you to see that we are still sort of going through the process. So 6.96 kips per inch. That is our capacity that we're going to use to lay out the weld. All right. Is everybody okay with this? Okay. Here's where things are going to get a little different. So I wanted to make sure everybody's okay with this before I move forward. Any questions? Okay. I'm going to skip to the next panel. All right. Do I need to go back or? Okay. Now, I am going to write up here real quick. I'm going to sort of write that number again, that's 6.96, because I want that sort of referenced. Okay. All right. So here's how we're going to go about laying out this connection, weld layout. Okay, so the first thing I'm going to do is I'm going to draw the angle out. Okay, so the angle looks something like this. That's a little long. That's good. And it's like that. Okay? So would you agree that on an angle, the centroid probably goes something about like that? It's not in the middle. It's going to be hugged closer to the back leg. All right? Sound good? I mean, centroids are going to be closer to the regions of higher material. Now, what I'm proposing is that the load, this load going like this, of PU equals 150 kips, I'm saying that we are assuming that that goes through the centroid. Okay? Now, here's where your bookkeeping skills come into play, and I want everybody to see where these values are coming from. Okay? This dimension right here, this is the 6 inches. Okay? That's the 6 inches.
I heard there was cake.
Help yourself.
No, there's plenty. I can eat some later.
Look at the picture.
I saw a picture.
Oh no, there'll be plenty.
It's the same people, right?
No, there's more people.
Yeah, but a lot of them are the same.
You gotta get it now, or it's not gonna be there.
I just want to say facial hair and lock.
Oh.
I wish you would've got your license out there.
Oh. I'll never hear the end of that one though. all, you will. All right. So I've drawn the angle out like this, and I'm being very specific in my proportions. In other words, I'm saying that this line is sort of continuing on, and I'm saying that, again, this dimension is the 6 inches. So that makes this dimension the 4 inches. Is everybody okay with that? Okay, because again, this angle is an L6 by 4 by 3/8. Now here's why I'm being so precise on this. Okay, now what I'm asking for is this. I'm saying that this goes through the centroid. So what I want to know from you is exactly. I want to know what this distance right here is. You got to get the manual out. Now who didn't bring their manual? Got his. If you now we're in the hold on while you all are looking, we're in the angles section of the manual. Do not look up the X sub P's and the Y sub P's. Those are related to bending, and we will talk about that later, but don't confuse those with the centroids. Yes, sir. Well, that's our assumption. That's what we're saying. Let me answer this a little more generally. If you don't have a load going through a centroid in general, then you have a combination of axial load and bending, and that is another interaction problem. But we haven't even talked about bending. You know what I mean? So it comes with time. So we will get there. There you go. All right. What is Y bar? 1.93. There you go. Exactly right. Okay. So this right here, this is Y bar, not X bar. Okay. So this is 1.93. Does everybody see that? Does everybody see why we're looking at the Y bar and not the X bar? If the angle was welded on its short leg, we'd be looking at the X bar. Everybody with me on that? Okay. All right, that's important, so I really want that to make sense. Now, here's what I'm going to do. For this connection, let's see what time it is. I got time. For this connection, I'm going to use 3 welds, because if you could do 3 welds, you can definitely do 2. All right. So since I'm assuming that the weld on the bottom is the longest, I'm going to draw them like this. So we're probably going to put a weld something like that. I'm going to assume we have a weld here. Now this is a transverse weld, and transverse welds are fine as long as you got longitudinal welds with them. And then we're going to have another weld that goes like this. Something like that. Okay? So each of these welds are going to be able to contribute a force. So I'm going to say F1, F2, F3. Okay. Now, of these 3 welds, which weld do we know the length? F2. We know the length of 2. F2 is 6 inches. Now, if I'm assuming that that weld is just a single line, F2 acts at a distance from the back of that angle of 3 inches. Is everybody okay with that? This weld is just a line right here. So I'm proposing, like, look, the weld's 6 inches long, right? Okay. If it's 6 inches long and the weld can withstand 6.96 kips per inch, I can calculate F2. And if I'm saying F2 is a force, it needs to be at a certain location. I'm going to say it's in the middle of that weld, which is right here. That's all I'm saying. So that's where the 3 inches came from. Everybody with me there? Okay. So let's calculate F2. So F2 is 6.96 kips per inch or over a distance of 6 inches. So what is that? Something like that, yeah. There we go. 41.76 kips. Sound good? Okay. Now, in order to determine F1 and F3, I'm going to treat this angle essentially like it's a beam. Okay? And that F1 and F3 value are the reactions. So in order to solve for those, I'm going to sum moments about, let's say, the back of the angle. And if I sum moments about the back of the angle, F3 goes through, and I'm solving for F1. Does that make sense? It's really not that bad. So we'll say summing moments equals 0. Bringing it back, right? So sum moments about the back of the angle. So about the back of the angle. The moment arm for F3, that's 0. PU goes this way times a moment arm of Y bar, right? So PU goes that way times Y bar. F1 is at a moment arm of 6 inches, and F2 is at a moment arm of 3 inches. Does that make sense? It's really not that bad, right? So just F1 times 6, F2 times 3. So the one unknown in this expression is F1. See what I mean? So PU Y bar equals F1 times 6 inches plus F2 times 3 inches. So F1 is PU Y bar minus F2 times 3 inches over 6 inches. So that is, what, 150 kips times 1.93. Oh, that's not multiplication, that's subtraction. Minus 41.76 kips times 3 inches. And what does that come out to be? $27.37. Do I have a second on that?
Yeah.
All right, so 27.37 kips. So you're telling me that weld number 1 needs to withstand 27.37 kips. My question to you is, how long does that weld need to be in order to withstand that? There you go. Exactly. So L1 is F1 over phi Rn, which is 27.37 kips over 6.96 kips per inch. What does that come out to be? I think we can knock this out pretty quick. 3.93. So in actuality, what would you use? Quattro. Now, I think we can do this pretty quickly. If I use sum of moments to determine F1 and L1, how would I determine F sub 3? Sum of forces. So the easiest, I mean, we can do the equilibrium if you want, but sum of forces is just going to say that F3 is PU minus F1 minus F2. Everybody all right with that? You know, if you got F1, F2, and F3 going to the left and you got PU going to the right, just subtract, right? So what is that? 150 minus 27.37. No, I got that backwards, but it actually doesn't really matter. 80.87. And how long is that weld going to be? Say it again. 9 inches? Yeah. F3 divided by phi RN. I got 11.60. So I say use L3 of 12 inches. So my point is, if you can do this, how would you do this connection if there was no transverse weld? You could literally use the same formulas and just set F2 equal to 0. You see what I mean? And then now, if you did that, weld 1 and weld 3 are going to get a tad longer because they got to make up for the loss in weld 2. But in the end, it's not hard. You know, it's pretty straightforward. So does everybody have this? No, you're fine, you're fine. I know I'm going a little bit over, but. All right. So, therefore, here's the answer. So, we have a 4-inch weld here, a 12-inch weld here, and a 6-inch weld there. So if you want to do your symbols, this is 5/16. Oh, goodness. That is messy. And then 5/16 and 12, and then 5/16 and 6. And there you go. That's essentially it. I'd argue you don't even technically need to put the 6 right there since you know it's along the whole length. So, but I'll go ahead and put 6. I know that's a really messy drawing, but I'm in a hurry because I want you all to not stay too late. Any questions? All right. And if you look on your homework, the homework problem is actually a little simpler based on the geometry. And you'll see what I mean when you actually start to get into it. That's all I've got for this. And I'll say this, that is everything on exam number 2. And that concludes a very significant portion of this class because starting Monday, things get different because we start talking about buckling. That's all I got. You folks who aren't in concrete, you have a good weekend. And again, thank you very much for the gift. I appreciate that. And I will have some here in a little bit. Thank you again.